Video, we're going to talk about vector-valued functions. So a vector-valued function is a type of function that takes in a real number and gives you a vector back. Okay, and in this class, we're going to be interested in the vectors being two-dimensional and three-dimensional. Okay, so the type of vector-valued functions that have a two-dimensional output, we're going to call those plane curves. They have, x of t and y of t. And their graph is an oriented curve in the xy plane. And when I say oriented, you see those arrows there. It's got a sense of direction depending on how the curve is parametrized. We'll see what that means, as we move forward. And then the type of vector-valued function is a three-dimensional output we'll call a space curve, and because it's a curve operating in three-dimensional space. And you can see there's a sketch of one of those right there. Now, the domain of one of these vector-valued functions is going to be the set of all real numbers t for which f of t is defined. And when we say f of t is defined means that all of the components are defined, in the sense like none of them are undefined because of division by zero or square root of a negative number or log of a number that isn't positive or something like that. So let's work a couple of examples, find the domain of the function. All right, so for this first one, I think I should probably, remind you about the rules. And I just mentioned them verbally, but I should probably write them down. So, if I've got 1 over something, I need to make sure that thing is not equal to 0. If I've got the square root or any even indexed root, I need to make sure that thing is greater than or equal to 0. And if I'm taking a log of something, I need to make sure that thing is positive. All right, so for kind of just like take this one component at a time, and I'll just say, all right, for log of t plus 2, I know that the inside, that t plus 2 needs to be positive. So I'm going to say t plus 2 needs to be greater than 0. But then also, I'm going to look at this 5 minus t over here. I'm going to say that's inside of a square root, so I'm going to say 5 minus t needs to be greater than or equal to 0. Now, in order for both of these components to be defined, I need both of these inequalities to be true simultaneously. So I'm going to say that the domain of this is where both of these are true, where t plus 2 is greater than 0, and where 5 minus t is greater than or equal to 0. And so what I'll do is I'll just kind of solve each of these inequalities individually. And that's going to give me that t is greater than negative 2, and also I'll need that 5 is greater than or equal to t. All right, so t is greater than negative 2 and less than or equal to 5. So negative 2 is less than t, which is less than or equal to 5. That's going to be the domain of f. All right, here's one for you to try on your own. Okay, figure out what the domain of G is, what your hypothesis is, and then check it against mine. You should work that with video pause, because bring in the answers here in a couple seconds. All right, there you go. So I took the inside of the square root and I made sure it was positive or equal to 0. So if 9 minus t squared is greater than or equal to 0, that's when t squared is less than or equal to 9. And you could think about this solving by graphing, making a number line and plotting, critical numbers or whatever you learned in pre-cal. Or you could just kind of think about it and be like, oh, okay, that's going to be between negative 3 and 3. And that's what I would prefer you do. Okay, for the one in the middle, the underlined blue, okay, it's a fraction. The denominator can't equal 0, so that means t can't equal negative 5. And then for the third component, the natural log of t squared plus 1, I need to make sure that argument, that t squared plus 1, that's a positive number, but t squared plus 1 is always positive, so this is always true. So I look at these kind of critically and think, okay, well, if t is between negative 3 and 3 and also not equal to negative 5, well, that negative 5 isn't really all that relevant. Then I just say that t is going to need to be between negative 3 and 3. All right, so you may have noticed that, this is kind of like what we did last year in Cal BC with the parametric equations, and it's exactly the same. Okay, it's just in AP Calculus we're restricted to 2 dimensions, and, no areas of surfaces of revolution or a couple other things that we're going to do in this class that we did in AP Calculus. Okay, but we're gonna do motion problems in here. And so just to remind you of some of the things that we knew last year, we know that the velocity is the derivative of the position function. And yeah, I guess I'm assuming that you've already watched the derivatives and integrals of vector valued functions lesson at this point. So like the velocity is the derivative of the position, and the acceleration is the derivative of the velocity, and therefore the second derivative of the position. The speed of the object is just like last year, even on the rectilinear motion, the motion along a straight line has the absolute value of velocity. Well, now it's just the length of the velocity vector. And you know how to find the length of a vector. We just do that with the first derivative vector. And then the arc length, or also the total distance traveled by an object moving along a parametric curve, it's going to be the integral of the length of the derivative, which is also the integral of speed, which makes a lot of sense considering that's been the formula kind of like all along, even since the beginning of calculus. But maybe before we go forward and work the examples, I'm going to remind you of why that formula is true, because it's a formula we're going to need, various times moving forward. Okay, so take the parametrized curve, and for now I'm just going to assume that it's a two-dimensional curve just for speed here. We're going to zoom in on a really small piece of it, right? We're going to cut it up into small pieces, and then we're going to add the length of all those together, and we're going to take the limit, and we're going to get an integral. So if I zoom in on that really small piece, I'm going to call that a delta p, small piece of arc length. And I'm going to have a delta y and a delta x. Okay, I know that delta x squared plus delta y squared equals delta p squared, but the total length is going to be the sum of all of these delta p's. And each one of these delta p's is the square root of delta x squared plus delta y squared. Okay, now to get this to look like an integral, I'm going to need to introduce like a t variable, right? So I'm going to multiply by a clever form of 1, delta t over delta t. But delta t over delta t doesn't do all that much for me. It would be a lot better if the denominator was the square root of delta t squared. Okay, because then I could go and do a little bit of algebra, distribute that in over the delta x squared and the delta y squared, which is also inside a square root, and rearrange it right in a certain way. So I could write it as delta x over delta t squared plus delta y over delta t squared. And then still holding onto that extra delta t on the outside. And then as I let the number of pieces of arc length go towards infinity and their respective t intervals go towards 0, this sum here will become an integral and will converge to the integral from t1 to t2 of the square root of x prime squared plus y prime squared with respect to t. And that's the formula that we're familiar with from AP Calculus. But if we think about it, from a vector perspective here, this is the length of the velocity vector, or the length of the derivative vector. So this is where we could go in and say, integral from t1 to t2 of the length of r prime of t dt. Alright, so for example, the velocity of an object is v equals cube root of t and 4t. Write an integral that represents the total distance traveled by the object on the time interval 1 to 3. Alright, so we've got the velocity vector. This will be really easy. Okay, so what we'll do is we'll say, remember that the total distance traveled is like the arc length. Oh, I need a thicker pen. It's going to equal the integral from t equals 1 to t equals 3 of the square root of x prime of t squared plus y prime of t squared. All right, so the cube root of t squared would be t to the 2/3. And then 4t, if I squared that, that would be 16t squared dt. Okay, that's the total distance. It's also the length of the curve. I want to tell you about the area of a surface of revolution, which is just one of those things that we don't talk about in AP Calculus because it's not in the course description. So imagine, rather than taking a region and rotating it around the x-axis, think about taking the curve itself and rotating it around the x-axis. You get kind of like a sheet. And if you want the surface area, well, this is something that we can find with an integral. I'm just going to assume this is a parametrized plane curve. And so what we're going to do is we're going to we're going to cut this up into really small pieces, almost like discs, when we did that in AP Calculus. And we're going to look at the area of that thing, and then we're going to add them all together. So if I look a little closer at that, it'd look like, kind of like a little ribbon piece. And then what I'd do is I'd kind of cut in, I guess I'd need to notice that it had a radius r and a width L. Now the L, that's going to be a little bit tricky, and I'll tell you about that in a second. That's where this one might go a little different from what you might expect. Okay, but now I'm going to go in and cut the thing. Okay, say right there. And then roll it out and take the area that way. Okay, so if I roll it out, I'm going to end up with a rectangle. Okay, and the length of it will be 2 pi r, the circumference of the circle, and the height will be L. Okay. But the issue is L is not just going to be delta x in this case. It's not going to be delta t either. It's going to be a small piece of arc length. And I'm not going to really give that a whole lot of justification besides to say that you can see that if the curve was really steep, we would be adding a whole lot more area than if it was, going in and being kind of shallow. And I think that's self-evident. And so L is one of those delta p's that I was just talking about, which is the square root of x prime of t squared plus y prime of t squared dt. Or really, I guess it's a square root of delta x over delta t squared plus delta y over delta t squared, square rooted delta t. But what we're thinking is that the total area is going to be the sum of all of these small areas. The small areas are 2 pi RL. And so as the number of those goes towards infinity and their respective widths or, lengths are going towards 0, that'll become an integral, and it'll be the integral from t1 to t2 of 2 pi RL. And I like this formula a lot. It's the most general. Okay, because we could do this around the x-axis, but we could also do it around the y-axis. And I'm not saying that a person couldn't do this around a different axis, but we're just not going to do that in our class. Now, the thing I was going to point out before I moved on all the way was r. I didn't really give r any discussion. The radius of that circle, or that little disc thing, what do you think? It's a frustrum, but that's a whole different discussion. I don't want to get into that here. Okay, this radius here is going to be the y-coordinate. So in this case, radius will equal y of t. But if I was rotating around the y-axis, the radius of these circles would be x of t. And so what I'm saying is, we can say if we can just draw a picture and figure out what r is, and we remember what L is, and we remember it's the integral of 2 pi RL, we can't go wrong. And kind of like the arc length integrals. Oh no. We're we're not going to be able to compute them without a calculator. It's very unlikely to be able to do these by hand. So we're just going to be settling with setting them up and not evaluating them, or in multiple choice, which of these is the right integral. So write an integral that represents the area of the surface formed by rotating gamma around the x-axis. We've got, hold on, I think there's something wrong with this. Yeah, this is the graph of 2t minus t squared and 2 square root of t minus 1, where t ranges from 1 to 2. Yeah, just had to triple check that. So if we're going to write an integral that represents the area of the surface formed by rotating curve gamma around the x-axis, I'll do that one in red. Okay, I'm going to draw a radius here. Okay, so it's going to be the integral from t equals 1 to t equals 2 of 2 pi RL. Y of t. Okay, y equals 2 square root of t minus 1. Oh, whoops. And then L is going to be the square root of x prime squared plus y prime squared. So I'm going to need to probably go back and do that. All right, I don't think you need to watch me do that. So I'm going to take the square root of x prime squared plus y prime squared. So 2 minus 2t, I'm going to square that, plus t minus 1 to the negative 1/2 squared. Okay, so if I square that, double the power, that's negative 1 power. T minus 1 to the negative first dt. And if I wanted to rotate gamma around the y-axis and find the area of the surface formed, it would be really similar. It's just my radius is going to be x of t, so integral from 1 to 2 of still 2 pi RL. It's just r is going to be a little different here, so that'll be the integral from 1 to 2 of 2 pi. R is going to equal x of t, so that's 2t minus t squared, and then L is going to be the same thing, 2 minus 2t squared plus t minus 1 to the negative first power. That's going to work out with the limit of integration. We're just not going to worry about that, right? That's why I said we're not going to be evaluating these. We're just going to set them up, right? So we're not going to worry worry about the fact that this might be an improper integral, and who cares? It's going to be all right. We're not even going to try to run it through a calculator either, because I don't think the calculator would like that. And this will be a good, particle motion example for us to end with. So object moves in the xy plane with velocity given by v equals 2e to the negative 2t and 1 over t plus 1 squared at time t, where t is between 1 and 5. Let p of t denote the position of the object at time t. What's the acceleration at time t equals 5? Okay, acceleration is the derivative of the velocity. So I'm going to be taking the derivative of velocity and getting negative 4e to the negative 2t and negative 2 times t plus 1 to the negative 3. Then say t equals 5, so I'm going to plug in 5. I'm going to get negative 4e to the negative 10, and what I'm pretty sure is negative 1 over 108. Right? To find the position function, I'm going to take the antiderivative of velocity, and I'm going to get negative e to the negative 2t, remember we got to be careful about the chain rule, plus some kind of constant, and negative 1 over t plus 1 plus some other constant. That's another type of antiderivative I need you to be careful about. Remember, it's not just going to be log of the absolute value of t plus 1 squared. We're going to think twice about our antiderivatives. And all you're going to know with the chain rule and all the derivative rules to double check your antiderivatives. And that's really what you need, especially when it's been a while. Okay, so we're going to need to figure out what these particular constants are for the information we're given. So I'm going to plug in 1 for t and 0 for x and negative 1 for y, and to figure these out, and then say, all right, well, p of t is going to be negative e to the negative 2t plus e to the negative 2 and negative 1 over t plus 1 minus a half. Okay. Next, it's going to ask about the speed of the object at time t equals 1. So to get the speed, I need the velocity. So it's going to plug in 1 into the velocity vector that they gave me. And then I'm going to compute the speed by squaring those components, adding them together, and putting it inside a square root. Okay. And, if we needed to, we could simplify it. It looks kind of tempting that there's things we could do with that because these are all kind of square, but you don't want to do that, right? We would have to combine with a common denominator, do some other stuff, and probably the numerator is not something we'd be able to simplify. We would be able to take the square root of the denominator, but, let somebody else do that. Okay, part D, if we're going to write an expression for the total distance traveled, we're going to integrate the speed. Okay, so we're going to be integrating from t equals 1 to t equals 5 on the length of the velocity vector. Okay, but we've got the velocity vector, so what that's going to be is integrating a square root of the sum of the squares of those components. So I'm going to get it set up, then I'm going to plug in the x component and the y component, 2e to the negative 2 and t plus 1 to the negative 2. And there it is, I've set it up. If all we're doing is setting it up, we don't have to make it too fancy, right? Just plug it in, and if we're selecting from multiple choices, we'll be able to see which one's equivalent to our setup one. Okay, and then for E, I recognize that if you just look kind of critically at this, the velocity vector is always going to have all positive components for any time t. But in a different situation where that wasn't true, the first step for this type of problem would be to find the value of t that they're talking about. So which of these describes the motion of the object as it passes through the point 1 over e to the 2 minus 1 over e to the 4 and negative 5/6? I think I don't know if you can see that clearly on screen. It looks a little blurry to me. But what you would do is you would notice how, okay, this is talking about t equals 2. Okay, I think it's easier to see from the first component that that's only going to be possible with t equals 2. And so we notice, okay, we're talking about t equals 2. And then we're going to check the velocity vector at t equals 2, because that's going to kind of tell us the trajectory of the motion, which is something we're going to talk more about in the next lesson. But we're going to look at v of 2, and we're going to get 2e to the negative 4 and 1/9. We're going to notice that both of those are positive numbers, right? The negative power of e, that doesn't make it negative, right? It's just 2 over e to the 4th. And that's a positive number over a positive number, which is certainly positive. Okay, and since the x component of velocity is positive, I know the object's moving to the right. And since the y component of velocity is positive, I know the object's moving up. So I'm going to choose answer choice D, up and to the right. Okay. And I think that's all I'm got for you. Between this and the previous discussion of derivatives and integrals of vector value functions, I think that's plenty. That's all you need. Go forward, practice on the examples. That's all for this video. Thanks for watching.